In this tutorial, we will be looking at how to implement and simulate operational amplifiers or op-amps in Microwave Office. We can use both ideal and non-ideal models in the simulator. Ideal models are built in, and we can also tweak some of their parameters to make them a little bit less ideal. But the main difference between ideal and non-ideal models is that with ideal models, you don't have an opportunity to specify the power supplies, and hence the output that you will get will often be unrealistic. So I very much encourage you to use real models as much as you can. However, I will go through how to use the ideal models in Microwave Office for completeness. So let's just get them out of the way. As usual, the first thing that we need to do is right-click on Circuit Schematics, select New Schematic, and then we'll call it Op-Amp Ideal. And we've got the usual canvas on which we can place our elements. If we press Ctrl L and we search by either name or description, we'll be able to find the op-amp quite easily. If I just Control-click on name and then search for op-amp, you can see that there's only one element that comes up, and that's the ideal op-amp, which is already in Microwave Office. So we double-click on that and we place it on the schematic like so. Now you can see that there is quite a number of parameters to be specified for this op-amp, and this can be quite overwhelming and confusing. And that is why also I think it's best if you just use a normal op-amp rather than this sort of thing. However, I will quickly go through how to tweak this element to be able to use it without being overwhelmed by it. If I click on the element and then right-click and show the help for it, you can see that the help shows you what is connected to every pin. And it is not too dissimilar from what we've seen in amplifier models, but there are quite a few things that complicate matters for us. Now, I don't want to go into great detail about these because I think it may be a little bit too much for you to take in at this stage. However, what we want to try and do is make this model as similar as possible to the one that we had in the lectures. So we want to get rid of this R1 here and this R2 here, and we want to completely ignore this pin 4. So we'll leave pin 4 unconnected, and we want to set R1 and R2 to values which mean that they won't matter at all. And because they are in shunt with the input, which is between pins 1 and 2, if we make them infinite, this means that effectively they would be like an open circuit. A shunt branch with infinite resistance effectively behaves like an open circuit. Again, as we have seen in the lectures, to make these infinite, you have to assign a value of 0 to them. If you scroll down a little bit, it'll tell you that if R1, R2 or R4 are set to 0, this means that they have infinite impedance. So I understand and I appreciate that this is not the clearest and most obvious way to do things, but this is the way the simulator works, and we have to be aware of these quirks. So we want R1 and R2 to be infinite, so they don't have any effect. They behave like an open circuit. So we'll have to set them to 0. So that's R1 and R2 sorted. We set them to 0, they become like open circuits, and we don't have to worry about them, or pin 4 for that matter. Then we will have just one resistor between our pins 1 and 2. And this will be our input resistance of the amplifier. So this we can then set to whatever we like. At the output, I'm not going to go through all of these parameters here. If you are really keen to understand this, then come and see me and then I'll explain to you what this is all about. But really, we don't want to bother with this very much at all, and there is an equation down here that explains what this is all about. What we want to reduce it to is just Vout equals M times V1 minus V2. What we want to try and do is make this exponential here disappear, and this can be done by setting various parameters to 0. What I'm going to do is modify this element in such a way that it becomes quite easy to use and that you're not overwhelmed by the number of parameters. I want to set it in such a way that the only parameters you'll be able to set will be the input resistance, the output resistance, and the gain of the amplifier. So let's close the help, and then we can double click on the element. This opens its properties. So we have got M, which is the gain of the amplifier. We've also got A, but this is not the same A as we saw in the lectures. Make sure that you look at the description for every element. So this is our DC voltage gain. So phase offset we'll keep to 0. We said that we want R1 and R2 to be infinite, so we'll leave them as 0. The output resistance in an ideal case would also be 0, so we can make it 0. And R4, which is our input resistance, is ideally infinite. So when we make it 0, in this case, this means that it's infinite. Also, R3 is the output, R4 is the input, and we get them kind of the wrong way around. So be careful with this. You can see how there are very many quirks to this model, and you've got to be careful on how to use it. The other thing that we can do to increase the clarity of this is go to the Display tab up here, and then we can choose to hide the parameters which we're not going to set, or that we have set and we don't want to have the opportunity to change by mistake. So we can simply untick the boxes here of those parameters that we don't want to display, and then we can simply tick the hide box, and this should hide them from view and make it a bit more difficult to modify them. So we've only left our gain M, and then our output resistance R3, and our input resistance R4. Then click on OK, and now you can see that things look a little bit better. Also remember that pin 4 now doesn't matter anymore. So here we are, now we've got our amplifier all set up. The next thing that I'm going to do is declare a couple of variables so that I can make things a little bit more similar to the lectures. To declare a variable, we simply go up here. You can see there is an x = y icon. We click on that, and then we can write our assignment. So we declare the name of the variable, say for example Ri, and then we say what its value should be equal to, and I'll say Ri equal to 0. This is because, remember, 0 in the simulator for the input resistance in this case means infinity. Then I'll get another equation, and I'll call this R0, and I'll assign 0 to this one as well, but in this case it will mean 0. So remember that R3 is our output resistance, so we need to assign this to R0, and then R4 is our input resistance, and so we assign this to Ri. Also, I'd like to declare a variable called A, which represents the gain, and initially I'll make this very big, say 1 million, and then I can simply assign this to M. Remember that all the variable names are case sensitive, so you've got to be really careful. So now we are almost there. We've got pin 4 that we can completely ignore. Pin 1 is our inverting input, V-, pin 2 is our non-inverting input, V+, pin 3 is our output, and pin 5 is our reference, which often enough will just be ground. So we need to specify the ground reference for an ideal model of an op-amp, because you don't have the voltage rails connected. And this is an issue because when you have voltage rails connected to an op-amp, the ground level is the middle point between those two voltage rails, and we will have seen this in the lectures. In this case we don't have the voltage rails, so we have to specify what voltage we want as our reference, and we'll just specify ground. So here's the complete model of the amplifier, and this is entirely ideal. We have A, which is really high, we can make it as high as we like, Ri, which is infinite, despite what this says. Remember that 0 for R4 meant that it was infinite. And also we have R0, which is 0, so our output resistance is 0. Totally ideal model of the amplifier. Now we would like to see what happens if we apply a voltage between our input terminals. Well, To do that, we need two things. First of all, we need a voltage source, and we can get that quite easily with Control L. And we'll just look for a DC voltage source, and then we'll simply place it right here. But notice, however, that the minus pin and the plus pin are upside down, and so we need to make sure that the polarity of our voltage source is also consistent with this. So let's right click and rotate it until we can align its plus terminal with the plus terminal of the op-amp and its minus terminal with the minus terminal of the op-amp. Now we also need to have a load resistance of some description. In this case, the value of the load resistance, of course, doesn't matter, because we have an ideal amplifier with zero output resistance, and hence it doesn't matter what we use as a load. But let's just get ourselves a nice resistance, again with Control L, and make it nice and high. And let's say that this is 1000 ohms, for instance, 1 kilo ohm. That should do the trick. And we need, of course, a ground reference here as well. Now we are applying a DC voltage. Because we are applying a DC voltage, we can simply add annotations to our schematic as we have done before. So we right click and we just say, okay, let's add an annotation and tell me what the DC voltage is at every node. Then click on apply and OK. Now simulate. You can see that we've got a 1 volt input across our terminal. Remember that the voltage gain of our amplifier is A times V plus minus V minus. So V plus minus V minus is of course 1 volt. A is 1,000,000, 10 to the power of 6. And you can see here that indeed we have 1 volt in input and 1 megavolt in output. Now you can imagine that this would be very unrealistic in real life. But this is what an ideal op-amp does. So it'd be nice to be able to tune this voltage source so we can move the slider and see what's going on in real time. Let's do it differently. Normally what we do is just click on the tune tool and then we click on here, and this allows us to then tune it by simply opening the tuner window. Well, let's do it differently. So I will untune it now, and then I double click on the voltage source and click on the Parameters tab, and you can see that there is a column here that says Tune. Put a tick on there, and then select Limit as well. And this allows you to select a lower and an upper limit for your tuning range, and also a step. So I'll say that my lower one will be 1 microvolt, which is E to the minus 6. You can write it like this, there's no problem, the simulator will accept it. And I'll say then my upper voltage is 1 millivolt. And my increments will be in steps of 1 microvolt. Now I also want to change the nominal value of my voltage source to the upper limit, really, because we don't want to go any further. So we'll make this 1 millivolt as well. So now we've got a voltage source which has got a nominal value of 1 millivolt, but we can tune it between 1 microvolt and 1 millivolt. Click on OK, and then simulate. Of course, we have 6 orders of magnitude difference between input and output. So at the output we've got 1000 volts, and at the input we've got 1 millivolt. We can then open the tuner, and then we can start lowering our voltage. And you can see that as we lower our input voltage, our output voltage is also plummeting. We are still in the region of about 300 volts, so it's really high. So let's take it right down to the bottom. Well, that's it. So now we've got 1 microvolt, and at the output we got 1 volt. We could handle that. That is actually physically feasible. But you see, I have to have a really tiny signal to be able to utilize the op-amp as it is. So in fact, if I start moving the slider up a little bit by small increments, we can see probably we can go up to 30 volts in output, and this would be doable, for example, with the power supplies in the lab. And this would mean that the input must be no greater than 30 microvolts, which is tiny, 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 tiny. And this is one of the reasons why we don't use the op-amp on its own normally. We use it in conjunction with other circuits, and we give up some of its huge gain for other purposes. And we will be seeing this in future tutorials. Now, lastly, just so that you know how this is done, I am going to show you how to perform a DC sweep. So let's simply close the tuner here, and also we'll get rid of the annotations by just clicking on them and pressing delete. And then we'll also get rid of this DC power supply, and we press Ctrl L. In this case, I want a DC power supply that's actually swept. And you can see that there is one here, swept DC voltage source. So this is what I want. I'll double click on that. Then of course I have to rotate it so that the polarity is consistent with that of the input pins on my amplifier. And then I simply connect it like so. Now I can again set a start, a stop and a step for my voltage sweep. So for the start, we'll use the same as we used before, 1 e to the minus 6, which is 1 microvolt. For the stop, we will use 1 e to the minus 3, which is 1 millivolt. And also we'll have an identical step to our tuning range, which is 1 microvolt. Now at the output, we use a voltage meter to be able to plot the output voltage. So we press Ctrl L and then type V_meter, and we place this on the schematic like so. We connect it across our output resistor, and this will now allow us to plot the DC characteristic of the amplifier, Vout versus Vin. So let's do just that. So we go on to Graphs now on the Project tab, right click, select New Graph, and then we'll call this Vout versus Vin. We right-click on the graph, go on to Add a New Measurement, and then we select under the non-linear measurements, Voltage, and in this case we'll select VDC. We need to specify the source for our measurement, and this is of course op-amp ideal, which is the name of the schematic that we set up, and then we can simply click on the 3 dots. This will open the schematic diagram. We can click on the measurement component, which is Vmeter VM1, and then on OK. Then we can specify that the input voltage that we set up, which was a voltage sweep as you may recall, we can use for the x-axis as is specified here. There are various options of course, but you have to select Use for x-axis. This way on the vertical axis, on the y-axis, you will have the voltage from the voltage meter, which is looking at the output voltage, and then on the x-axis you will have the voltage from the swept power supply, and this allows you to plot Vout versus Vin. So click on Apply and then OK. Now simulate. You can clearly see here that we are going with input voltages which range between 1 microvolt and 1 millivolt, and our output range is 0 to 1000 volt, which is of course extremely unrealistic. So in this tutorial we explained how to tweak the model which is built in Microwave Office for an ideal op-amp, and you can indeed use it when it's set up in the correct way, but be careful when you use it, make sure that everything is set up correctly. You can simply use this schematic and do a save as, and then you know that the op-amp is in the right shape. And also the other thing that you can do is see what happens when your gain is no longer this high. Or you can also change your input resistance and see what happens when you do that. Or your output resistance and see what happens when you do that. So although it is an ideal model, it still allows you to look at what happens when the gain is not as high as it should be, which can happen with higher frequencies, when the input resistance is not as high as it should be, or when the output resistance is not as low as it should be. But what it does not allow you to do is to look at the effect of finite DC power supplies on the output of the amplifier. And this is clearly reflected in this graph, which shows that you are totally unbound in the output range.